forgets, if you can't make it to class or you're stuck in 6 feet of snow somewhere, this stuff will be available to see after class. So where we're at is alcohols, talking about their chemistry, talking about some review of things that you've seen before, getting back into the swing of things, right? The first week of class is always a bit of a pain because it's cold and it's miserable, and put your phone down at the back. It's no fun getting back into school. So let's get into it. We left off talking about the structures of alcohols and trying to differentiate between primary, secondary, and tertiary. That's up to you. That's fairly straightforward. Of course, with any type of organic molecule, you've got to be concerned about their properties, their physical properties, as well as their chemical properties. As you head towards bigger subjects like biochemistry, you'll see that the interplay between hydrophobic and hydrophilic ideas becomes really important. The organic structure in a molecule can make it insoluble in water, which can be a problem in biology, right? And in medicine when things start to precipitate. But a lot of this stuff is very simple. There's nothing too tricky here. So to start off today, we'll talk about these physical properties of alcohols compared to other compounds that you've seen. So on the slide here, you've got 3 molecules, very similar. One of them's an alkane, one of them's an alkyl chloride, one of them's an alcohol. And you can see now that the range of boiling point is actually very broad. In organic chemistry, we usually say, okay, the playing field in terms of temperatures that you can achieve in a lab is -100 to about +200. Below -100 isn't much use to us. Things start to freeze. Above +200 degrees, things start to break apart. Molecules start to decompose. So we have this 300-degree sort of playing field to be able to do organic chemistry in terms of refluxes and boiling things and stuff like that. Why is it so broad here? -89 for the alkane is very low on the left up there, and +78 is a big difference, even though the molecules haven't changed by much in terms of their size, in terms of their formula weight, and really in terms of the type of atoms that are involved. So why is the alkane such a low boiling material? Intermolecular interactions. Now I got 2 answers I heard there. One of them because it's a gas. Now that's telling me that it's a gas. We know it's a gas because the boiling point is -89. That's not telling me why. And again, the difficult part for many people in this class is understanding the why. Why is it such a low boiling material? And the answer is because it has weak intermolecular reactions. Because boiling is all about breaking molecules not apart within themselves, but breaking them away from their neighbors. Can you close the door at the back? Thanks. You've got molecules next to each other, and the more interaction you have, the more difficult it is to break them away from each other, and that's boiling or freezing, whatever you want to call it. And in this case, ethane has very weak interactions because we don't have any dipoles. So dipoles are important. Dipolar interactions held things together last semester. They still will here. And as you head up to chloroethane, the boiling point goes above 0. So now you have an interaction based on a dipole. Where would you put delta plus in that molecule? In the middle molecule, where would you put a delta plus? On the alpha carbon, the one with the functional group, and that would be delta minus. And all of a sudden you have this distribution of electron density that gives you a dipole. And then you have more glue that will hold the molecules together between each other, right? And you must understand here the difference between intermolecular and intramolecular. This is all about intermolecular forces between different molecules. The more glue holding them together, the stronger the intermolecular forces, the more energy it takes to break those forces, the higher the temperature of the boiling point. Now all of a sudden it gets dramatic. I mean, that is a big difference. Going up to +78 right there. Any ideas? What does this molecule have on top of it of simple dipole interactions? Hydrogen bonding, all right? So hydrogen bonding plays a large role in the boiling points of alcohols. It's incredibly important. And you can see, again, thinking about biology, the solvent in biology is water. And if you can hydrogen bond to something, you have a decent chance of dissolving in water, right? So it's all heading somewhere. Now, you can see here a system very similar to stuff that you did last semester in class when you in the lab when you started trying to dissolve alcohols up, and you saw that some of the small, low molecular, small chain alcohols dissolved up quite easily. Methanol is completely soluble in water. Ethanol is pretty much completely soluble. But as the chain gets longer, they became insoluble. You got separation, you got oils and layers and stuff like that. And that's all based on this idea of hydrophilic and hydrophobic. Now, we haven't used those words too often, but we need to start using them and understand what they mean. So at the bottom over here on the left, you have methanol. And it has a balance between what we call the hydrophilic region, the methyl group, and the hydrophobic group, and also the hydrophilic group, which is the OH. Okay, so remember, something that is philic likes something else, so hydrophilic means it likes dissolving in water. When you have a small molecule like that, the alkane part, the alkyl part, isn't so important. The OH group wins. But as you move up to the higher alcohols, as you did last semester in lab, you'll find now that as the chain gets to be 6 carbons, 7 carbons, 8 carbons, it starts to win. Okay? The importance of the alkyl group now is increasing, and the importance of the OH group is decreasing, and so you might expect this to become less soluble in water. And you actually saw that in lab. You should remember that from last term. Now, that's a big problem. That can be a big problem. Exactly 1 year ago this week, there was a chemical spill in West Virginia. You might not remember this, right? It was at the Elk River in West Virginia, and they spilled thousands of gallons of this chemical. Now, you may not have seen this before, but at this stage in your chemical lives, you ought to be able to look at that and tell me an awful lot about why this was such a problem, right? This caused all sorts of lawsuits and all sorts of problems for the people involved. The vice presidents, I think, are indicted under various EPA laws for being slack and letting this stuff get into the river. As soon as it gets into the river, it goes elsewhere, okay? And so they had this boil alert for about 3 weeks in West Virginia, and it caused lots of problems. So from a chemical perspective, look at that compound. Do you expect this compound to be soluble in water? No. No. Now that's a problem, right? If it's not dissolving in water, where's it going to be? Now look at the density. The density at the bottom says 0.9074 grams per mil. Is this stuff going to sink in the water or float on top of the water? It's going to float. So you've got this oil layer on top of the water floating around the rivers, getting into all the ecosystems, causing all this mess. Now that might not be such a problem if over time things started to evaporate. You know, and things start to dissipate and go elsewhere in the environment. But look at the boiling point there. Do you think this is easily evaporated or not? Absolutely not, right? So this stuff was horrible. They cleaned it up eventually, but it's a big problem, and it was down to sloppy management and sloppy maintenance at the site, right? And for some reason, they decided to build this plant right next to a river, and so as soon as the building started to decompose and the containers started to break, this stuff got into the river. And you can see, you know, West Virginia, if you've been down there, it's a beautiful part of the world, and these types of things are really serious problems. Okay, so alcohols can be impactful in terms of industry and environment, and they are very, very useful. But what I want you to be looking at is you have some sort of knowledge of these things already just by looking at the simpler boiling points. Now, what we'll do for the most of today is go back and review. And my aim today, by the end of class, is to get into the reduction chemistry using borohydride, which is coming up in lab next week, and so that you're ready for that. You know what's going on there. We know that alcohols are acidic. What's the approximate pKa of an alcohol proton? It's about 16. Now, I'm going to say about. Last semester we said pretty much 16, right? This semester we get a bit more subtle because we're going to look a bit more in depth at the structures and think about what the impact of those structures will be. Is it 16? Is it 17? Is it 18? And that's not a big difference. You might think, well, what's the big deal? That's not a big difference. But as you become a more highly trained scientist, that is a big difference, right? Those are powers of 10. That is an order of magnitude, so that is a big difference. So when we think about alcohols, the acidity of the alcohol depends upon a very similar property to what we just talked about. Having that OH group there can hydrogen bond to things, but it can also bond to a base. The fact that the hydrogen in these alcohols is delta plus makes it immediately attracted to a negative base, or a base with a lone pair that is going to be looking for something positive to attack. And we will use these things as starter materials to deprotonate and make this material over here. And we've mentioned this word in the past, but now it becomes more significant. The alkoxide is the conjugate base of an alcohol, and we'll use that term to describe it as such. Alcohols are not as acidic as phenols. Why is the pKa of a phenol 10 and the pKa of an alcohol 16? What can you do with a phenol that you can't do with an alcohol? Resonance stabilization at the conjugate base stage, right? So that comes into play again, and we start worrying about what those numbers mean. So we'll do some acid-base chemistry. We'll think about some of the old properties from last semester, some of the old ideas, trying to review this stuff so it sinks in and hopefully it makes more sense now. We looked at, in great detail, the relative acidity going across the periodic table and the relative acidity going down the periodic table. And we built up some very simple ideas that then became useful in other areas. The size of the anion made a difference. Delocalization in the anion made a difference, okay? But also electronegativity. So if you go across the periodic table at the top, and you think about these compounds over here, which is the carbon-based material, it is the worst conjugate base. It is the least stable. If you put a negative charge onto carbon so far, right, the rest of this semester we'll do a lot of carbon-negative chemistry and make it more stable by adding electron withdrawing groups. But if this is simply CH3-, it's a very, very, very unstable species, right? It does not like having a negative charge because it's low electronegativity and it's unstable. So as you move across the periodic table and you go to the next one, nitrogen, it becomes a bit more stable. But it's still a very powerful base, right? What is the pKa of NH that you're used to? 38, right? High 30s. That's not very acidic at all. You really have to work to take that proton off, and you have to use a very powerful base to do so. But you'd certainly see a significant drop in the instability of the species because you've gone from carbon, electronegativity of what? 2.5 to nitrogen with electronegativity of 3, right? It's much better at handling the negative charge. So then you go across to the other side here, and we start to see that alkoxides are bases that you can isolate. They are bases that you can put in a bottle and leave on the shelf for a while, but they're still quite reactive. The pK of the conjugate acid is 16. That means the base is quite reactive, and that will be useful to do all sorts of stuff in the near future. We did use those already in things like E2 chemistry last term, and we'll be reviewing some of that stuff in the near future. And then the most stable on the right-hand side, F minus, Cl minus, Br minus, the ones that can handle the charge because they are so electronegative. So you have this idea now that, yes, alcohols are very useful because you can do all sorts of things with them. So far, we have eliminated them. We have done acid-base chemistry with them. And now we're just reviewing some of those ideas. So far, so good? Okay. Now, in terms of your understanding of acid and base chemistry, if you've forgotten the pKa's, you must go back and look at them. You must understand where they come from so that we can use them very quickly and not have to worry about going through all that stuff again. We've now said that the very weakly acidic materials, typically the proton is bonded to a non-electronegative element or a weakly electronegative element. So the pK up here between 45 and 50 is all based on the fact that the carbanion that you make, the conjugate base, is so unstable because of the weak electronegativity. And then you move to the NH2 groups. We'll see them being very useful in the near future. Those will be nucleophilic and they'll be basic. And they're weakly acidic. They're not as bad as the alkanes, but they are still weak acids because of the fact that the NH bond isn't that polarized. As you start to polarize the bond even more, we get down to something really useful, 15 to 18. We'll describe why those numbers are different in a few minutes. And then on the right-hand side, as we get to the halogens, you're aware of those already. From freshman chemistry, they're always strong acids. So what we'll need to do here is deprotonate. Some of the most useful chemistry of alcohols involves taking the proton off to set something else up. And we did some of this already last term. We took off a proton from an O-, and then we attacked an electrophile. We went after methyl bromide, went after ethyl iodide, and we did SN2 chemistry. And that will make an ether. And the next chapter coming up after this is ether chemistry, in which we'll see that again. So we'll have to review SN2 and SN1 and some of the limitations. Now, what do you know about this stuff? Is that a strong base or a weak base? It's a very strong base. Any ideas why? And again, at this point, you know everything. Everything I'm asking you, you know the answer to. You just have to come up with it. It's unstable, but that's telling me the same thing. You know, that's really the statement there is the same thing. It's reactive, it's unstable, it's a powerful base. They're the same thing. What we're trying to dig at now is why. Why is that such a powerful base? What constitutes a powerful base? Can it delocalize? No. So that's one factor against it being a weak base. Right? Is it a big species or a small species? Is H- small or big? Small. Do you like having a negative charge on a small species? No, that's counterintuitive. That goes against the rules from last year. Is it a highly electronegative element, hydrogen, or weakly electronegative? Weak. All those factors build up to that being a pretty potent base. Right? That's a pretty powerful base. On the other side, the pK of this conjugate acid is about 45. That gives you an idea of how strong a base that is. So in this type of reaction, which we'll set up to do something called a Williamson ether synthesis in the near future, the first step is deprotonation. And your choice again your job again is to choose the right base. If I choose hydroxide here, how does that change the outcome? If I swap out this base and I put hydroxide in there instead, how does that change this process? It will be in equilibrium. You will go over here and you will go over here because the conjugate acid that you produce from this is water with a pK of 16. You have the same strength of acid and base on the left as you do on the right. What would K be approximately for that process? 1. Now that's okay if that's what you want, but that's not usually what we're after. If you want complete deprotonation of that alcohol right there, you choose the appropriate strong base. And a very simple one to get hold of and use is that hydride. So NaH will deprotonate an alcohol irreversibly and set this up so that we just have the alkoxide. If you're not happy with the acid-base stuff, you don't remember it, go back into that course pack from last year, do that acid-base problem set, right? I think it was chapter 3. Go look at that stuff again and just review that stuff because it really is important now. A second possibility for doing this is something that is kind of fun to do, but it's a little bit more dangerous, is to take sodium metal. Now, the mechanism for this is beyond the scope of the course, but it is basically a reduction. Basically, you're putting electron density into the system by using a metal. Sodium transfers its electron to the oxygen, and you make O-. You've got to be careful here because you bubble off hydrogen gas, which is flammable, so you've got to be careful when you set these things up. But you have two methods now. If you have access to this stuff, which most organic chemists would have, we have a couple of bottles of this stuff, that's probably the safer way. If you don't, you just have that, you can do that as well. So they both result in the same thing. They both result in the alkoxide, and that alkoxide now is important itself. What was related to ethoxide that we spent a lot of time talking about last semester? A bigger variation of alkoxide, a bigger variation of TB-toxide. Oh, so I gave it away, didn't I? TB-toxide, right? TB-toxide was very useful as a base because it was so big. So these are how you make them, and then we can use them as reagents. We'll use them as nucleophiles, and what else is a nucleophile? A nucleophile can also be a what? A base, right? So there's going to be lots of arguments about when these things become acids and when they become bases. So there's nothing new there, really. Look at these two systems. pKa differences now. You have 18 on the left, and you have 10 on the right. I think all of you who are here and have passed the first semester should get this pretty quickly. The pattern recognition, the idea that on the right you can do something that you can't do on the left. Why is the pK on the right lower? Now, let's be careful. Resonance when? Resonance where? In the conjugate base, right? In the conjugate base. When you take the proton off, you can delocalize the charge on the right, but you can't delocalize the charge on the left. And so we can draw resonance structures. Again, if you're a bit shaky with resonance structures, practice, ask, get it organized now, because a couple of chapters later, we do resonance structures everywhere. It's very, very tricky. So you can see now that the species on the left, the charge will be localized, and the species on the right, the charge will be delocalized. But let's go a bit further. We just said on the previous slide that alcohols like this have a pK of about 16. But we're now saying that cyclohexanol has a higher pKa. And if you're interested in, you're here for a reason. If you're interested in medicine or pharmacy or biology or engineering, precision is important, right? These little differences make a difference now. They should be something you appreciate and understand. Why do you think you have a 2-unit difference? That's 100, right? That's orders of magnitude different. You're changing this from a primary alcohol, and this is becoming a secondary alcohol. And all of a sudden, the secondary alcohol is weaker. It's not as acidic. So we want to start expanding your ability now to put into practice the things that you know. And so if you saw that, you'd have to try and have a go. And you can't just say because one's a primary alcohol, one's a secondary alcohol. That doesn't explain anything. That just tells you what type of alcohol we're dealing with. So what would you do? Look at those numbers. What would you start to do to answer that problem? What would you draw the conjugate base? Good, you're starting to think. Right? You would draw the conjugate base. And the conjugate base of the cyclohexanol derivative looks like so, right? The charge is localized on that oxygen. And the conjugate base of this guy over here is a primary alkoxide. So that's the first thing you do. Then you start to consider everything we did in chapter 3 onwards from last year. What constitutes a weak conjugate base? What type of things will stabilize a conjugate base? Resonance. You can't do resonance in either of those, so it can't be that. So we're looking at the negative charge on the oxygen and asking the question, which one is more stable and why? What factors in these molecules stabilize a negative charge or destabilize a negative charge? Mr. Homan. Solvents, let's say they're in the same solvent. Hyperconjugation, you're getting on the right idea now. Hyperconjugation will make a difference. We might not call it hyperconjugation as such, because that's usually reserved for positive charges and radicals and things that have an intermediate type species. But what's closely related to that we talked about last term? Brock de Angelo. It's similar to that. That's what I just said. Okay? Thank you for reaffirming what I just said. But that's exactly what we're after. We're trying to get the subtleties now. What we're trying to get at, and what I think your brain is trying to tell you, is that this thing pushes electrons towards this, and this thing pushes electrons towards that, because they're both electron donating groups. Alkyl groups were always electron donating. Now, what's the effect of having a secondary system here versus a primary system here? Do you think you might get more electron donation from the secondary system? Yeah? You might get more electron donation from that because there are more bonds around. Or you might destabilize that because of that. That might destabilize the negative charge. Or solubility, if they're in the same solvent, maybe this isn't so easy to solubilize because it's bigger, similar to TB-toxide last year. So those things make sense, and it is a pattern, and it does add up. It's not sort of different so much from last year, but those are subtleties that you should be okay with. We now have a 2-unit pKa difference based on those types of properties. So, have a look at this one. Again, you know the answers. We saw this last year. You see two alcohols, both of which are very closely related. One is ethanol, one is 2,2,2-trichloroethanol. And we can see here now that the pKa difference, again, is quite dramatic. That 4-unit difference, you know, if you've ever been in an earthquake, the difference between a 2.0 earthquake and a 6.0 earthquake is quite dramatic, right? And that's what this is. It's a logarithmic scale, like the Richter scale. So that's a big difference in pKa's and a big difference in acidities. Why is this so much more acidic than that? Give me some ideas. Induction, right? This is now electron withdrawing or electron donating? It's electron withdrawing, right? Because chlorine's so electronegative, it's pulling electrons away from this end. What effect will that have? Well, number one, I'd argue it makes the proton a bit more positive because you're pulling electrons away from it. But then on the other side of the equation, because we always had to consider both sides of the equation, what effect will this electron withdrawing group have on a negative charge? Will it stabilize it or destabilize it? It should stabilize it, right? Anytime you can spread charge out is a good thing, even if it's only through the single bonds. So the electron withdrawing group now has this ability to stabilize the anion, also makes the proton a bit more positive, and you can see here definitely that's going to add up to a much more acidic molecule. So subtle things, but things that you should be okay with and be able to handle. Everybody all right? Mr. Huber? Everybody all right? Who's over there? Trish, you all right? Okay. There's the argument from last term, just to finish it off. It is consistent. In this case, you're looking at solvolysis problems, you're looking at donation problems. The fact that the base got bigger is going to make it a bit more difficult to solubilize, and therefore is less stable, and therefore more basic. And if it's more basic, its conjugate acid is less acidic. Should be okay with that. Right. Think about these molecules. We're going to see a lot of these in the near future. Probably after spring break, not too near. Look at the systems here. And again, you know the answers. If you look at the top, you'd have to ask the question, all right, which one is more acidic? Is this more acidic or is this more acidic? And we're talking about the OH proton. Do the same thing. Scribble. Organic chemists are notorious for scribbling. Write stuff down. Usually the answer falls out. It's like mathematics. Just try and work something out. If you take this proton off here and you make this, give me a word that describes the charge here. Localized is a good word. It's localized. It isn't going anywhere. You cannot spread it out. As opposed to on the left, yes, you can delocalize this because it's an enol, and then we'll talk about enolates a bit better, the negative species, and you can do all sorts of delocalization here, as shown by those resonance structures. So which of those two acids is more acidic, left or right? Which one did we say? The one on the left, okay? This is the more acidic, because you can delocalize the charge. Very simple things, very subtle things, but again, stuff that we know. Again, much of this is review, getting ready for using this stuff in synthesis, and we already mentioned these things in great depth last year, so this should just be trying to get it back up to speed. If you want to try and make an alcohol, you have all sorts of alternatives, and you'll get more alternatives in this chapter. You can start out with a primary system, and you can start out with a base or nucleophile like hydroxide, and you can do substitution chemistry to replace the Cl with the OH. If you replace something, it's substitution. Now, how do you know this is SN2? Give me some factors here that lead you to think it's an SN2. It's a primary system. So what is good about a primary system in the SN2? It's accessible. It's easy to get to. It's not crowded out. So this is now, you know hydroxide as a base, but in the right circumstances, it can be a nucleophile as well. If it's accessible, you're going to do substitution chemistry because that gives you single bonds. If you do elimination chemistry, you get pi bonds. They're not as strong. So we now get substitution. How would you test this? What experiment could you do in the lab to make sure this is definitely an SN2 reaction? Add more nucleophile. If you add more nucleophile, what should happen to the rate of the reaction? Increase. It should go faster. Right? If it's bimolecular in the transition state to the product, that should, in the rate determining step, it should go faster. So then we can change that. We can go to a tertiary system. The secondaries are always problematic, right? The secondaries always gave you mixtures, but primary and tertiary are fairly clear cut. A tertiary system is not going to give you substitution with hydroxide. Why not? Why, if you threw this stuff in this case, why wouldn't that give you an SN2 outcome? It's too crowded. It's way too crowded, and it will change its character and become a base. So if you use this at high pH and you were to use hydroxide in the presence of that alkyl chloride, what mechanism would take over? E2, right? The E2 would take over. So that's kind of a dead end. We can't use this for substitution chemistry with basic conditions. So what we can do instead is very similar to your lab experiment last year, where you were advised to isolate the alkyl chloride very quickly. Don't leave it hanging around in the water, because then you get solvolysis. Then the reaction would go backwards. So this reaction now is SN1. What does that involve? What kind of steps? Leaving group breaks off, form a carbocation, and then something comes in to help. And if you have solvent there, you have water as a lot of, water is the solvent, so there's lots of it, then you're going to be able to trap that quite easily, and that will give you this. And again, how would you tell this wasn't an SN2? How would you tell it was an SN1? Add more water, and what should happen to the rate? Won't change, because that's not involved in the rate determining step. Yep, things that we brought with us. Okay, these slides are going to get quite dense. Why? Because we've already done it. This is review. You can go back and see now, and in this slide you've got the references to the book. You can go back and see where these things were used. We need that toolkit. We developed a whole bunch of stuff last year that we could now use to do chemistry. You need to bring those things with you. So in this example, we start out with an alkene, and we add something, dilute sulfuric acid. And what are we adding? What's actually adding in that reaction? It's adding overall, what's hydronium will be involved, but what's actually getting added overall? Water, H2O. So this is a hydration. And what would you think the first step would be? You're an acid, if pH is low. What is the first step of that reaction? Protonating the alkene. Okay, so things are starting to wake up now. We protonate the alkene. But you have a choice of where to put the proton. You have a regiochemical issue. Where does the proton go? The primary carbon or the secondary carbon? It goes to the primary carbon, and why is that? Because the secondary carbocation that you would produce is more stable. What rule was that? Markovnikov. That's Markovnikov addition. You can't forget those things now. So yes, we can do that, then we can trap with water, and that will give us an alcohol in a Markovnikov sense. Well, the problem with some of the chemistry we did last semester was that things got a bit crazy and things started to rearrange. The molecule at the end didn't look like the structure at the beginning, because carbocations rearrange, right? If you have a secondary cation that can become a tertiary cation, it often does that. If you have a strain cycle that can open up, it often does that. They're a problem. So we developed a method that avoided that process. We used oxymercuration. We made that three-membered ring with the mercurinium ion, and then we trapped that with water, then we reduced off the mercury, and that allowed us to produce alcohols without any rearrangement. The key there was probably no carbocation. If you don't form a carbocation, it can't rearrange, and that was the way we did that. So go back and look. And then finally down here, everybody's favorite, hydroboration, right? Hydroboration. If you don't remember it, go look at the final. It was on the final exam. Be okay with it. We didn't use BH3. Why not? It's too complicated, right? It involves horrendous stoichiometry. So what did we use instead? Parachute. We used that 9 bbm material, B with the parachute attached, and that enabled us to get nice, clean, anti-Markovnikov addition of water, which is hydration, and we put maybe the OH group on the primary carbon instead of the secondary carbon. So I would advise you in the next day or two, just go and look at that again. Make sure you're familiar with those ideas and that you're comfortable with how to use them and why to use them. Anybody got any questions? Samson, any questions? You're just sitting there chilling out, right? Okay, that's fine. All right. Now, recitation. Again, if you're not in recitation, ask yourself why not. It's only an extra hour, and it's important. We started doing this in recitation. We'll do it again today. The idea of manipulating carbon in the lab or in biosynthesis, or what we might call metabolism, so that we can do things like release energy or store energy, or we can build bigger compounds like we would in a pharmaceutical sense. We're going to have to spend a lot of time this chapter and for the rest of the term thinking about what state carbon is in and what state we need to have it in our product. And by that I mean oxidation states. So those of you who've had recitation already have seen this. Those of you who have it this afternoon will see it this afternoon. If you're not in recitation, you'll have to come and ask me in office hours, because this can be tricky, but it is useful. We'll start off on the left with maybe the simplest organic molecule that we have, methane. And Brock, the biggest source of methane is what? It certainly is, our bovine friends. Okay? And you can harness this from various natural sources and then use it as fuel. And you can use it as a starter material to do organic synthesis. If you add it to bromine and heat it up, you make methyl bromide. All of a sudden you have a leaving group, you can do all sorts of other chemistry. But we would argue that methane here is fully reduced. So we're going to go back and worry about some terms from freshman chemistry, maybe even from high school, I would hope. This idea of what reduction means, what oxidation means. So I was always taught the little acronym, ORE, right? Oxidation is the removal of electrons. But oxidation could also be the introduction of oxygen, or it could be the removal of hydrogen. It can be quite complicated. And I've always thought this analogous to the acid-base argument. When we start acid-base chemistry, there were always protons around, correct? Right? Bronsted-Lowry definition of acids, we're always looking at protons, and even the more narrow definition, we're looking at hydroxide as the base. And then we expanded that to the Lewis definitions. The Lewis acid-base definitions really open things up because you don't need protons to be acidic. Yeah? Tell that to the freshmen, it'll just destroy them. You don't need protons to be acidic. You just need to be able to accept electrons. And to be a base, you have to donate electrons. So that just opens the world up to be able to do chemistry. This is somewhat similar in the sense that this idea of oxidation reduction is poorly understood. You get some very simplified definitions that are very narrow early on, but to be able to do this subject and subjects after it, you have to be able to expand that idea. So you're all used to oxidation involving oxygen, correct? Or reduction involving hydrogen. Well, that's not necessarily the case. If we expand this out to involve just electron density, then oxidation is the removal of electron density, and reduction is the introduction of electron density. So the way we work this out, from a very simple method or technique, if you like, is look at this sequence of events. Look at this sequence of compounds. We started out in 3719 here. We are now doing this in 3720. We will then move into that, and ultimately that. That's the sequence of events for the rest of the term. But they're all related, but they all differ by electron density, where the electrons are. And to get this started, I'm going to spend 2 minutes on this so that everybody's seen it. And then if you're not comfortable with it, ask the questions, because what we'll do next relies on this. In this case, think about electronegativities. What is the electronegativity of H? 2.1. So I might write that down. And I've got 4 of them. And the middle atom, the carbon, what's its electron density? 2.5. I've done that so I can consider where the electrons are in each of these bonds. In each of those CH bonds, where are the electrons? Closer to C or closer to H? Closer to C. Closer to C. Now, I've just said that oxidation is the removal of electron density. If you're pushing electron density towards something, that's the opposite. What's the opposite of oxidation? Reduction, right? Those hydrogens are reducing that carbon. They are affecting the electron density around that carbon in a way that they are pushing electron density towards that carbon. That's why we'll call it fully reduced. Not just because it's all hydrogen, but because the electron density is closer to the carbon. Now, what happens if you swap out one of those hydrogens for something more electronegative? What will happen to the electron density? It'll be pulled away from the carbon. Oxidation is the removal of electron density. So as you put some atom on there that's more electronegative, you're oxidizing that central carbon. So if you go across here now to the second molecule, methanol, I've got 3 of these hydrogens, and I've got 1 oxygen. And this guy is more electronegative than carbon. So in that one bond, that one CO bond, the electron density will be closer to O than it is to C. Compared to the methane on the left, this carbon now has less electron density. If oxidation is the removal of electron density, this is now more oxidized than it was. So that process to go from here to here is going to be described as oxidation, OX, in a box. And to go backwards will be called reduction. At this stage, yes, you can use the old arguments about it being introduction of oxygen or removal of hydrogen, but when we see examples in which there are no oxygens available, but we're still getting oxidation chemistry, that's where we need to be okay. So far, so good. Now, I'm going to get rid of the noise. Is it okay that this is now more highly oxidized again? That central carbon is now bonded twice to oxygen and only twice to hydrogen. So compared to its precursor on the left, it's now more highly oxidized. Kyle? Not really. What will make a difference is the introduction of the pi bond, because now we could argue, all right, over here, delta plus, but over here, more positive because of resonance possibilities and delocalization of the pi bond onto the O. We drew a resonance structure last term in which O had a negative and C had a positive. That's a very positive carbon. A very positive carbon has lost electron density, so it's highly oxidized. Does that make sense? Yeah, just has to click this stuff. Once it does, it's not difficult. And as we go further, we are now removing one of these hydrogens again, replacing it with an O. So that central carbon should be losing more electron density, therefore is more highly oxidized. And then the ultimate at the far end is carbon dioxide. Okay? When you metabolize and you expel carbon as carbon dioxide, it is the most highly oxidized because the middle carbon is bonded 4 times to O. Dominic? Yeah, all of this stuff so far in this direction is oxidation. And we'll also worry about the opposite direction, which is reduction. It is in each case. We have a method to quantify this, or at least to have a way of labeling some of these things so that we can talk about them quickly. What we're going to say, you have to listen to this and be very careful. Mr. Gotham, you with us? Is that a Manchester City shirt? I hope not. I'm going to give every atom that is less electronegative than carbon a -1, and this is not a charge. Write that down. This is not a charge. We never see -4 carbon. That's silly. This is just a number that helps me understand the effect of the hydrogen on the central carbon. It is pushing electrons towards the carbon because it's less electronegative than carbon. Conversely, you could say the carbon is pulling electron density towards itself and away from the hydrogen. So if we're pushing negative electron density towards the carbon, let's give it a -1. So what we'll say now is that when you add all that up, the oxidation number, the oxidation state of that carbon is now -4. We go across now. We have changed this. We now have a +1 because it's now pulling electron density away from the carbon. It's making it more positive, if you like. What if you had a carbon attached? What number would you give that? 0, because it doesn't do anything, right? So now I've got +1, I've got -1 for this, -1 for that, -1 for that, and that, I hope, comes out to be -2. And you can use this very quickly, and I will test you on this at some point, to be able to describe that as an oxidation event. The number becomes less negative, we're heading towards positive, we're heading up in terms of oxidation values, and that will inform you and give you a clue as to what you need to do when you're trying to do a synthesis. Do I need to do an oxidation, a reduction, or neither? This will help you out. Okay, where does 0 come from here? Twice +1 for oxygens, you just count it twice, and then -1 twice for the hydrogens, that gives you 0. Further across, -1 +1 twice, +1 should come out at +2. Finally, +1, +1, +1, +1, 4 times, +4. So you're not going to get -5. You're not going to get -6. If you get -7, no, that's not good. All right, we're looking at -4 all the way up to +4 and things in between. And we'll start using this as we work our way through reactions to be able to understand what it's used for. So the book has another method of doing it. I don't particularly care for this method, but you can try it if you don't like my method. I've always used the plus-minus idea with the identity or the electronegativity identity of the atom attached, and that seems to work nicely. And this is all about counting electrons. This is going kind of backwards because you have to go back into Lewis dot structures. I think it's more time consuming. So either way works, you get the same ideas and the same values. It's entirely up to you. So moving on, with that in mind, we can now start to look at chemical reactions in a little bit of a different way. We can think about what we need to get to use. We can start understanding things and not guessing when we need to do chemical reactions. So I've got a system here which is a cyclopentanone, and it reacts with hydrogen with a metal catalyst, very similar to last term, and it gives you cyclopentanol. And I'm just going to expand this out by putting the hydrogen there. That's what adds. So overall, I've added H2. And I need to worry about whether this is a reduction or oxidation, or neither, in terms of it being a chemical reaction that I can actually describe. So if I look at this carbon on the left, using that set of values that we just developed, what's the oxidation value of that carbon? Carbons are 0, oxygen's +1, so what is it? +2. Not charged. That's its +2 oxidation state, comparing all the atoms attached to it. Now on the right-hand side, what is the value here? 0. +1 from O, -1 from H that we just brought in, and 2 zeros for the carbons. Is that 0? Are we okay with that? That is now 0. So we went from +2 to 0. We're going backwards now. That's not an oxidation anymore, that's the opposite. But just to make sure that this fits and this works, think about the definitions that you should have brought with you from high school and from freshman chem. You are you are adding H, no doubt. You're introducing hydrogen. That is by definition a reduction. Are you removing oxygen? Think about this carefully. The oxygen is not leaving, it's not disappearing, but where it was bonded twice, it's now only bonded once. So yes, you're losing some oxygen, right, in that sense. And then electron density-wise, what is the effect of the oxygen over here? What will it do to electron density around that carbon? Push it in or pull it out? Pull it out. What about over here? What will the hydrogen do? Push it in because it's less electronegative. So the oxidation state has definitely changed. And you definitely have either oxidation or reduction, and your job is to work out that it's a reduction. And if you weren't given this, and all you were given is that, and you had to decide what to use, that might inform you about what to do. You're not going to use an oxidant. You're not going to use an acid, stuff like that. You need to use a reductant. And that will start to become apparent as we work the next few chapters. Everybody okay? Okay? Should start to get a bit more involved now, but a bit more interesting, and things should start to fall into place, I hope. Well, okay, that works fine. That type of chemistry is great, especially on big scale because it's cheap. In the lab, we typically wouldn't do that type of reduction. And this is stuff that was developed during and after World War II, and it's now becoming very important chemistry because these reagents that you probably have read about, I would hope you've read about already, are starting to be used in fuel cells. These are a way of generating hydrogen gas. Hydrogen gas you can use as a fuel, and so people are starting to use these solid pellets of these materials to generate hydrogen and therefore propellant. We use them in the lab as a reductant. And what I want to get through today with my last 10 minutes is introduce this idea, introduce the structures, worry about why they do what they do, and then hopefully see a couple of mechanisms, maybe one mechanism. So here's a chemical reaction that you will do. You will do this next week in lab. You take camphor, which is a ketone, and you reduce it with borohydride, which is a solid white powder, and you reduce the ketone to the alcohol. Things you should be noticing now. Starting material here is a ketone. There is still no Y in ketone. There never was. There never shall be. And what we get here is an alcohol. And what type of alcohol is it? How do you classify it? It is secondary. That's important. Secondary. If you're not happy with what that change was, it was very similar to the last slide. We brought in an H. Now we're trying to get more sophisticated. You made it through the first round. We're in the second round now. What do I need to bring in? If I'm attacking, look at the differences. I've got an H apparently going here, and I've got another H going there. Logic now. The H that goes to the O. Do you think the H that goes to the O is H plus, H radical, or H minus? You don't need to guess at this stuff, just consider it and think about it. Look at how electron dense that oxygen is. Think about its delta. Is it delta negative or delta positive? Is that oxygen delta negative or delta positive? It's delta negative, isn't it? It's delta negative. So would you put an H plus on it or an H minus on it? H plus, of course you would, right? So at some point, we're going to have to bring in H plus. Same question, different part of the molecule. What is the electronic characteristic on that carbon? Would I put a delta plus there or a delta negative? Delta plus. So if you need to bring a hydrogen into it, do you bring in H plus or H minus? H minus. So now, we're going to be using hydrogen, or H, in different ways. H minus and H plus. We have many sources of H plus. Hydrochloric acid, sulfuric acid, water, all those things will give you H plus. What we haven't developed so far is H minus, right? We have used it as a base, but now we need to use it as a nucleophile. And one of the best examples of that is this. This is sodium borohydride. You'll use this yourselves next week. Be careful with it. It's a powder. Don't get it on you if you can help it. And it is basic and it is nucleophilic. And then what we do here is use it as nucleophilic hydride. If you use sodium hydride, not a great nucleophile. It's very, very basic. But if you control the reactivity by having it next to a boron, this becomes a hydrogen nucleophile. It becomes H minus. And we'll see now that the mechanism is very simple. You're going to take borohydride. It's the equivalent of H minus. And that H minus is going to attack your carbonyl, and you're going to get a new bond between C and H. Now, it's a new mechanism. We haven't seen this one. You are adding something, and that something is a nucleophile. So let's call it nucleophilic addition. The first big mechanism of this semester is nucleophilic addition. And really, the whole term can be made up of two big mechanisms. Nucleophilic addition, nucleophilic acyl substitution. That'll be Friday. But right now, we are beginning to develop nucleophilic addition, which is not anything we did last year. You need a nucleophile, you need a carbonyl, put the two together, nucleophilic addition. Now you'll notice that the solvents here, give me a word that describes those solvents. They are protic, right? They are definitely protic. They are polar and they are protic. So going from left to right, I need hydride in the form of borohydride, and I need a proton. I don't need a strong acid here. Okay? A strong acid, in fact, would destroy the borohydride. Water's acidic enough, and that gives you the product. So it's a two-step process. The hydride comes in, we get a nucleophilic attack, 2 electrons go up onto the O, which makes sense because it's electronegative, and then you get this in the middle. And that in the middle is an alkoxide, the same as it was when we deprotonated an alcohol. That alkoxide can then get protonated. If you choose the right solvent, I think you might be using methanol or water next week, similar type of idea. It is acidic enough to make this work. And then you get the product, which is reduced. It's a secondary alcohol in this case. So a ketone gives a secondary alcohol. What do you think an aldehyde gives? Think about R, C double bond O, H. You bring in an extra H, what type of alcohol do you get? Primary, right? You'll see that very quickly on Friday. So what I want to finish off with is the electronic nature of this thing. I want to talk about quickly why this thing is so useful. If you look at the periodic table, where is boron? It's to the left of carbon, all right? So if it's to the left of carbon, is it more electronegative than carbon or less? Less. It turns out it's less electronegative than H as well. So in this system, I'm going to redraw this. I'm going to maybe try and draw this here. I'm going to draw B, H, and I'm going to put it in square brackets. And the overall thing is negative. And each of these BH bonds is now polarized. But it's polarized in a sense that the H is more electronegative. So we're going to put a delta negative on an H. Is that a good thing or a bad thing? Not so good. It's small. Doesn't really want that charge. That makes it reactive. It's reactive enough to react with a ketone or an aldehyde, and it will give you a reduction product. So this species now is the equivalent, again, of H minus. And we can use it very easily to reduce aldehydes or ketones. I have on my website all these mechanisms drawn out with some audio. You can listen to them. And this, again, is the prescribed mechanism for how you do this. You will start with borohydride. It will behave as the equivalent of a nucleophilic hydrogen, H minus. It will attack the carbonyl. We could argue that the boron that's left over has 3 bonds, therefore it's Lewis acidic, and it can coordinate with the oxygen. We might change this a little bit on Friday, but this is what's happening. And at the end of the day, you've seen those things before. You saw that with the hydroboration mechanism last term. You've got a number of hydrogens left over, each of which is delta negative. You can do this 4 times. If you do this 4 times, it's starting to sound like BH3, right? It's starting to sound a bit tricky because you're doing things again and again and again. But that would give you this, which is the product. That then needs to get hydrolyzed by the solvent in this case, and you end up with an alcohol product. In this particular case, why am I using a squiggle? It's a chiral center. It's racemic. What does that tell you about that starter material? Give me a word that describes that starter material. Prochiral. So on Friday, we'll do a bunch of examples, and then we'll crack into some different reagents, and we are into the semester. Okay.